Hello, everyone, and welcome to today's e-showcase, Design and Startup of Kansas's first Sidestream Deammonification System. I'd like to thank Viola for sponsoring today's event. Today's presenters are Gina Kadava and Daniel Hurt. And Gina is Operations Engineer with Johnson County Wastewater, and she is the O&M Engineer and has over 15 years of experience in wastewater treatment. Daniel Hurt is the Regional Sales Manager with Veolia Water Technologies, and Daniel has worked in the water wastewater industry for over 18 years and 13 years at Veolia. He has a BS in Biology from West Georgia University. And now I will hand our presentation to our presenters.
Thank you, Regina.
And Daniel, you can go ahead and share your slides, and we will be able to see your slide deck.
Did it not share?
Not yet. So go ahead and select that, either the share at the bottom.
Okay. Try this again. There. Okay, got it now.
There you go. Thank you.
All right, I think I got it now, guys. Thank y'all so much for your patience. This is Daniel Hurt, Regional Sales Manager for Veolia Water Technologies. Today, we're going to talk about the design and startup of Kansas's first deammonification system. First of all, where does the deammonification side stream treatment process fall in the flow path of a overall wastewater treatment plant? As you can see, the top half of this slide shows the mainstream treatment portion, and the bottom half of this slide shows where side stream treatment falls into play. Side stream treatment deammonification process, it is applied to the dewatered centrate from anaerobic digesters. And this flow stream, as is stated here, it's a really small percentage of the total wastewater treatment plant's inlet flow, 0.5 to 1% of the wastewater plant's flow, but it is roughly 10 to 20% of the nitrogen load. This is just with standard anaerobic digester centrate. As you can see, a little bit higher nitrogen load with a THP component, but with that nitrogen load, roughly the ammonia concentration is between 500 and 1500 kilograms per liter of nitrogen that you can treat with the side stream deammonification process, that you return that reduced ammonia load back to the head of the plant. A few deammonification principles. Most everyone has seen this curve before. It's conventional nitrogen removal curve, where you go from nitrification and denitrification, going from converting ammonia to nitrate by putting the bugs under aerobic conditions by adding air, and then from nitrate to nitrogen gas by adding carbon. So that's the conventional nitrogen removal process. We're in the side stream, the deammonification anammox bacteria for nitrogen removal. It's a shortcut method in order to achieve going from ammonia to nitrogen gas. As you can see, by using this anammox bacteria, you reduce the amount of air required, and there's no external carbon required to convert from ammonia to nitrogen gas. So showing where how conventional nitrogen removal would be summarized, going from ammonia to nitrogen gas, is more oxygen consumed. There's a significant carbon requirement. There's more CO2 emissions produced, and there's more sludge produced. By using the anammox bacteria for nitrogen removal, there's less oxygen consumed, roughly 60% less oxygen consumed. There's no carbon requirement for this shortcut method for nitrogen removal, less CO2 emissions and less sludge produced. And it's roughly 1/3 the cost of pounds per pound of nitrogen removed. Why biofilm technologies? Why the ANITA Mox process with biofilm as a biofilm kit technology? First of all, deammonification with non-biofilm technologies by using the anammox bacteria, it can be difficult to retain this anammox bacteria on sludge and granules, difficult to retain and control it at times under with these types of methods. It can, with a non-biofilm technology, can require a champion operator to be dedicated to the process with a higher level and skill set to operate various components and pieces of equipment. The non-biofilm technologies inherently have more equipment and require more maintenance. And those non-biofilm technologies are sensitive to environmental changes. They're sensitive to flow increases, decreases, loads increases and decreases from what's designed for, and various other parameters that would come into the reactor. And these non-biofilm technologies, they have a tendency, they can be prone to upsets and washouts during these types of conditions. So the better way of being able to use the anammox bacteria is to put it on a biofilm. You want to attach that biofilm on a media carrier. And so by doing this, you're easily retaining your anammox bacteria on the carrier within the reactors. As you can see, the carriers that we use are roughly the size of 2 quarters stacked on top of each other. This house is a protection shelter for the anammox bacteria during startup time, during idle periods, during periods of upset. And by having the biofilm attached to a media carrier, there's a maintenance-free component with regards to this process. We have over 30 years experience using biofilm growing on carriers and over 1,000 systems worldwide. Now, a few of the treatment system components for the ANITA Mox deammonification process. First, we'll talk about the 2 different configurations that are available to treat the side stream flows. There's the MBBR configuration for simplicity. It's a flow in, flow out process. With the MBBR, all of your AOBs are in the biofilm, and so all of your anammox bacteria are on the biofilm as well. So it's a flow in, flow out process. The IFAS configuration is used to treat the more challenging concentrations and loads coming in. We typically use this when we treat THP centrate. By using the IFAS configuration, you're incorporating mixed liquor back into the ANITA Mox reactor. So there's basically a 2-sludge system. So the AOBs are in the mixed liquor flowing around inside the reactor with your anammox bacteria on the carriers. Just a general summary of the maintenance-free components of the ANITA Mox process. The MBBR configuration, as I mentioned, you have the K5 media. They're plastic carriers. They're designed and extruded from plastics, from virgin plastics that can be used for the life of the process. So there's a longevity component to the media. We use media retention sieves. These are rolled perforated plate stainless steel that are attached to the walls of the reactors. So they're made to allow the carriers with the anammox bacteria to stay within the reactor at all times. And these are perforated plate stainless steel, so there's no wear items as a stainless steel media retention screen. The aeration system is a medium bubble configuration. This is a design, Anox Collins design that we design ourselves. It's constructed of 304 stainless steel. It's basically has stainless steel pipes with laterals with holes drilled in them. So there's no wear items on the air grids. There's no diaphragms to change or anything like that. So it's a 0 wear item for the aeration system. Also have instrumentation and controls. You have a PLC control panel. You have ammonia nitrate probes. You'll have DO probes. You'll have pH probes. as part of monitoring the performance of the system. Also, you have top entry mixers that will be used intermittently within the operation of the ANITA Mox process. These mixers are designed to not damage or harm the biofilm carriers. So they're specifically designed to mix media. And finally, blowers. I say if necessary, because obviously most of our installations, they have existing aeration capacity on site from the secondary aerobic process. So typically there is enough air already available to be able to provide the appropriate aerobic conditions for the anammox bacteria. But if there's not enough aeration capacity, dedicated blowers can be provided. Just touch briefly on one of the key traits of the ANITA Mox process, its robustness and resilience. As you can see, under various scenarios with regards to upset conditions, from power shutdowns to not being able to feed the reactor, you introduce this scenario to the ANITA Mox reactor. The recovery time is less than a shift. So it's roughly less than 8 hours for the process to recover during a condition of overfeed, that you're increasing load to the plant, to your ANITA Mox reactor. The recovery time, once things go back to the normal design conditions, it's roughly half a day you can achieve back to your steady state removals. With regards to aeration, no aeration, say you lose your aeration source, your blowers go down, the system can rebound within a half a day to a day, and so that you will be able to achieve your normal percent removals after the conditions have been aeration has been restored. With regards to excess polymer feed, this is a common one that's been tested and has been realized in full-scale installations. With regards to having excess polymer in the dewatering process, the system will recover within a half a day to a day once the polymer laden centrate passes through the process. The percent removals from the ANITA Mox process goes back to the normal percent removals once that system has been flushed out with the flow going through the reactor. Just a few advantages and benefits of the ANITA Mox process. It works well within pretty much any geometry tankage available. Any various sidewater depths from 10 to 30 foot sidewater depth. They can be round, they can be rectangle, they can be square. We can retrofit pretty much any geometry tank. Compact designs with maintenance-free components. The media, as I mentioned, is virgin extruded virgin plastics, so it's a non-wear item. The media retention screens and the aeration system are stainless steel, so there's no wear components on the media retention screens or the air grids. No anammox washout. The biofilm is housed on the carriers, so there's greater protection from shocks and load increases, toxicity, polymer upsets, and various conditions that can happen in the dewatering process. So the biofilm is protected. It's got a safe house and a shelter within the media, not prone. And also the anammox biofilm is not prone to biofilm disintegration because it's protected and sheltered within the media. The anammox bacteria, by being attached to the carriers, can tolerate various conditions, as I mentioned, high range of TSS, polymer, upsets in DO, and various other conditions in the dewatering process. So once the shock system passes through, the ANITA Mox reactor goes back and gets normal steady state conditions, and you're back to achieving your normal percent removals. No need for media replacement, as I mentioned. Media is extruded from virgin plastics, and it's the life of the system. We've got carriers that are the same age as the same carriers in systems ever since they've been installed. The ANITA Mox process, as I mentioned, it is a resilient and works with various dewatering schedules, as I talked about earlier. It can handle various flow conditions where you don't have flow going into a system, when you have various intermittent flows coming into a system from various dewatering schedules. So you actually can take vacations, basically, with this process. We have conditions. We have a program. We can be able to pulse air within the reactor by not feeding reactor with citrate during when you're out of town. And so there's a vacation period time without harming your anammox bacteria. And finally, the ANITA Mox process, typically there's no need for micronutrients. Every wastewater is different, but our experience to date is that several of our installations have micronutrient systems there as an insurance policy, but to date they have not used their micronutrient feed to date. So it's there basically as an insurance policy. So I would say typically there's no need for micronutrients. With regards to installations here in the U.S. for the Sidestream ANITA Mox process, we have 6 operating installations here in the U.S. and a total of 10 that are either operating and or under design and in being commissioned right now. So we're not new at this. We've got experience doing Sidestream treatment with the ANITA Mox process. And now I'll turn it over to Angina. One more slide here about the Tomahawk Creek wastewater treatment plant. This is the plant that we've gathered here to talk about today. As you can see on the map here, Johnson County, it's basically on the Kansas side of suburban Kansas City. And the Johnson County water team, they selected the ANITA Mox process for its robustness and operational simplicity several years ago. And so we went through a design with them and with their consultant to put together a proven technology for the Tomahawk Creek wastewater treatment plant. And I'll turn it over to Angina now.
All right, thank you, Daniel. So yes, this is what Tomahawk treatment facility looks like after the upgrades. This is a 19 MGD design annual average facility that can treat up to 3Q through the biological processes. Wet weather flows above 3Q are pumped directly to a set of 8 pile cloth media filters for auxiliary treatment. For liquid treatment, Tomahawk has primary clarifiers. Primary effluent goes through 4 BNR trains for nitrogen and phosphorus removal using biological processes. Secondary effluent, along with any wet weather flows, are then pumped to the filters for further treatment and finally disinfected using sodium hypochlorite. For solids treatment, the primary sludge is pumped to gravity thickener. The thickened primary sludge is combined with the waste activated sludge and sent to RDTs to be co-thickened. The co-thickened sludge is stabilized using the anaerobic digesters that you see at the bottom of the slide there. And the digested sludge is finally pumped to centrifuges for dewatering. The dewater cake is trucked out for land application, while the centrate is pumped to the Sidestream Deammonification process for further treatment. The treated centrate is then pumped upstream of the BNR tanks. So the point with all this description is to just focus on the size of the Sidestream ANITA Mox process at our facility. Although the footprint of this deammonification process is small compared to the BNR tanks, it is designed to remove about 15 to 20% of the nitrogen load at design conditions. Next slide, please, Daniel. A close-up of that Sidestream process. Most of the process, in fact, all of the liquid process is below grade. We have 2 reactors that receive equal volume of centrate from our centrate wet well. You can probably see some of the mixers sticking above grade in the middle of that slide there, but for the most part, it's all below grade. The building to the right has the controls for the process, the HMI, and the heat exchangers to provide the anammox bugs with a constant supply of warm centrate. What you don't see on this picture is are the 2 chemical tanks that are associated with the process, like Daniel mentioned about. The first is sodium hydroxide tank that is provided to help with alkalinity supplementation when needed. And there is also a small micronutrient tank, which could be used when the bugs are struggling to get their nutrients from the centrate. So far, like Daniel mentioned already, we did not have to use either of these chemicals. The design flows and loads are on the next slide. Yeah, they're summarized on this table here. The main point to convey here is that at design condition, the Sidestream process will be able to treat about 20% of plant's nitrogen load at less than 1% of the influent flow. The table also lists some of the startup flows and loads in the right column there. Flow-wise, we are there for the startup flows, but influent ammonia load-wise, when you look at the influent ammonia to this Sidestream process, we are still running a little behind. Currently, we are about 10% of the nitrogen load compared to the 20% number that's presented on this table. Our ultimate goal is to get about 85% of ammonia removal using this Sidestream deammonification process. Performance plots on the next slide. We are currently running at an influent ammonia concentration of about 600 to 700 milligram per liter. As a comparison, the process is designed to go up to 13 to 1500 milligrams per liter of ammonia. And as I said earlier, this ammonia concentration translates to about 10% of the influent ammonia load to the plant. Once the centrate is treated, the treated centrate has about 200 milligrams per liter of ammonia. So in effect, the process is reducing about 5 to 8% of the nitrogen load from the Sidestream process. With very little aeration energy and really no additional carbon addition. Looking at it from a different perspective, the plot on the right, the process is currently treating about 60 to 70% of the influent ammonia that it receives. As I mentioned, our ultimate goal is to get to 85% of ammonia reduction, which we are right now seeing happening as our influent ammonia concentration goes up. Another way to track the performance is on the next slide. Thanks, Daniel. So this slide here is a little busy, but I'll try to work it through slowly. So during our early days of plant startup, the sludge that was generated at the plant was pumped off-site for biosolids treatment. And as a result, there was not much nitrogen, or there was no nitrogen load that returned from the Sidestream to the mainstream. At that point, the facility was able to consistently stay below 8 milligrams per liter on effluent nitrate concentration, which is currently our target. Once we started processing the sludge on site, there was an increase in the effluent nitrate concentration. We averaged about 8.5 milligram per liter of effluent nitrogen during those initial months before the Sidestream process started up. Since the startup, the nitrate concentration have come down, as you can see on the plot, and there is no additional aeration energy or carbon that's added to the BNR tanks during the startup process. And then, like in July and August, we were doing some MLR, or the mixed liquor recycle pump optimization. So you would notice that the effluent nitrates went up again a little bit. But the main point I would like to convey from this plot is that our effluent ammonia kept decreasing as or after this Sidestream process was started up. Daniel, back to you.
Okay. Yep. As a summary, the key takeaways of the ANITA Mox process as a biofilm technology, it's an easy to operate and start up and maintain system with expandability with regards to the biofilm on carriers. So it says expandability. There's most time room for adding additional carriers to be able to increase your percentage fill of your process. The ANITA Mox process is a proven, simple, stable, and robust technology and process. The MBBR system is a flow in, flow out configuration. So, but inherently, it's easy to operate in nature. With regards to the process, it's reliable and resilient to handling various upsets and high levels of fluctuations and shock loads coming into the process, as you would experience, could potentially see it in your dewatering system. So the biofilm protected on the carriers can withstand these fluctuations and shocks. And finally, it's operator-friendly technology. You don't need a champion operator. It can be operated as a committee. So basically, the MBBR is inherently an easy to operate process. So there's really no specialized process that you need to know and understand to be able to operate the ANITA Mox process. With that, well, I'll turn it back over to Regina for any questions or comments. I see there's a few that have popped up on the chat box as we've been talking.
Yeah, this has been great. Thank you so much. We do have a couple of questions that have come through. Go ahead and select the everyone option, and please send us your questions so that we can ask questions to Daniel and to Anjana. So our first question is, what was the startup duration? Was there a seed with anammox carriers from other plants?
Anjana, I'll start with this one.
Yeah, go ahead.
Yeah, I'll start with this one. Yes, there was a seed anammox bacteria on carriers that was used to start up the Tomahawk Creek plant. Typically, we start with 5% seed, and which was used for the Tomahawk Creek wastewater treatment plant. Anything additional, Anjana?
That's what I wanted to say too. So we started with 5% seed, and right now when we open those reactors, we'll look through those reactors. You can see that the anammox bacteria pretty much propagated everywhere on each of those carriers. The duration of startup, I would still say that we are going through the startup process. The bacteria it looks like the bacteria is well established. It's just going through and making sure that we have the right concentration of influent ammonia load to the reactors. So that's what is going through right now. But bacteria-wise, the process looks to be well established.
And just as a summary, general startup is typically within 2 to 3 months. Once you're seeing during a normal startup like that, when you're seeing you're closer to design flows and loads coming in.
All right, great. And we've got another question here that says, heat exchangers were mentioned. What is the target temperature for the centrate feeding the process, and what is the initial temperature? What is the fuel source for heating?
I'll start, and John, just briefly as an overview, the typical design temperatures, specifically for Tomahawk Creek, was design temperature was 25 degrees C, but typically the range is between 25 and 35 degrees C would be the centrate temperature.
Right. Yeah. So this process is downstream of anaerobic digester. So we have a pretty consistent source of warm centrate coming in, but being in Kansas, the temperature fluctuates significantly, right? So the heat exchanger is just an additional insurance to make sure that we have that consistent supply of warm centrate to the reactors. For the most part, we were able to not use those heat exchangers. We started in April, and through summer we didn't really need to use any of those, but we'll follow up and see how it goes through the next winter. The source of fuel for heating at this plant, it's still the natural gas that we are using.
Okay. And we've got several inquiries from Eric. So he said, you said something about heat generation. He just wants to talk about the HXs and what is the heat source, which I think you've just addressed.
Right. So the heat exchangers, Eric, we are like when we have a centrate or wet well, centrate holding wet well that, and from there the flow goes through these heat exchangers and to our reactors. For now, those heat exchangers are like, it's just flowing through the heat exchangers. There is no heating per se at this point. But like I said, it started during warm temperatures. So we'll see how it goes, how the temperature fluctuates during winter, and we'll have to probably kick in our boiler to heat the centrate.
Okay. And I'm just going to say Eric's again, because I think his may be a backup from what he was asking initially. Is the natural gas used at the backup as well?
I believe that natural gas is the source of for our boilers here at Tomahawk Creek. Yeah.
Okay.
Yeah.
Okay. And then we have another question that came in. How do you hope to optimize the system to hit the target 85% removal, such as what variables are being adjusted, temperature, DO, etc.?
So at Tomahawk, the entire facility is going through a startup right now. So getting the digesters to optimize, to make sure that they do their right level of stabilization, I think that would be a key to make sure that we have a higher concentration of ammonia coming out of them, which will then be used to feed our Sidestream process. So a key to that would definitely be to look at the influent source, the influent ammonia to these Sidestream reactors. When you look at the effluent ammonia out of these reactors, we are able to get to that 200 to 150 milligram per liter. But I think it like mathematically it would work better if we have a higher concentration of ammonia to begin with. I believe there are other options that are being explored right now with regards to optimization of the Sidestream reactors to make sure there is 85% removal. Daniel, do you have anything else to add to that?
Exactly. I know that process is ongoing right now as part of the optimization during this startup phase to being able to drive down that effluent ammonia out of the ANITA Mox reactor. That is ongoing and being done as we're speaking right now. But I don't have the exact details of what all the changes and adjustments are being made, but that is going through as part of the startup optimization right now.
Okay. And do you have any need for foam control?
So at Tomahawk, I can go with Tomahawk, and Daniel, you can explain on that more. But at Tomahawk, during the very initial phases, maybe the first few weeks, we did see some foam that was formed. We did get a supply of defoamer, but I believe we never had to use it because eventually the foam subsided and the process caught up. So to answer your point, there is a defoamer at our facility, but we never had to use it.
And with regards to how the equipment is designed, there are airlift pumps strategically placed within the ANITA Mox reactor which sprays water from the ANITA Mox from the reactor out onto any potential foam to knock down the potential foam. It's basically a spray header system, which is an airlift pump. So I think there are 3, maybe 4 per reactor at Tomahawk Creek. So that's one mechanical piece of equipment that we've designed to keep foam down within the process. And unfortunately, it's below grade, so you can see it.
All right, so we've got one from Edward that says, are the basins always covered? Do you need to scrub the air for odors?
I'll take this one, Angina. No, the reactors are not, are most of the time, they're not covered. They're open to air. They're open to air. We do have installations even indoors. So it does not have to be covered. Obviously, heat, you want to maintain your heat within your reactor, but as long as you're getting cinch rate continuously into your reactor at the design temperature, we have an installation out in the Rocky Mountain West where they're open reactors, and so they don't have to, and they're able to maintain their design temperature within the reactor. But with regarding to, I think, what was the last one, Regina? I think it was.
It was, do you need to scrub the air for odors?
No, there's no odor control. No odor control devices or equipment is needed. Like I said, we've got have an installation that's indoors, and there's no need to have any sort of odor control systems.
Okay, great. And then there's another question here that says, why not use biogas instead of natural gas for heating?
I think that's a very good question. I don't know. I have an answer to that. Yeah, I can get back to you on that question actually. But I do want to say that, like, yeah, it was probably the cost probably had to do like there has to be some cost component associated with that to make that decision. But honestly, yeah, I don't have the answer to that. Sorry.
Okay. Well, we have another question that is from Robert. He states, you mentioned the micronutrients aren't usually needed, but what's the trigger for determining whether they do?
Typically, there's a set of lab analysis, obviously, that can be done to determine of various micronutrients that the anammox bacteria needs to be able to perform at its maximum capacity, at its best, and stuff. So, but typically, just for from a macro standpoint, we usually, that's usually something when you're looking at treating the cinch rate and you're not getting your anticipated percent removals, you're automatically your first guess would be, okay, maybe there's something insufficient within the wastewater stream, and then we would go back and do the lab testing of the dozen or so micronutrients that the anammox bacteria needs to determine, and then add the necessary amount of chemical. But typically, we would look to see, okay, if we're not getting performance that we anticipate, that's usually one of the checks that we will do if once we've gotten stable operation within the process. Like I said, to date, I think we only have one installation that uses it, and they just use it because they want to get higher performance out of the reactor.
Okay, great. We still have time for more questions. We've got one more here. We've got a couple more, actually. What is the intent of the mixers in the MBBR tank?
Yeah, I can start on this one. At Tomahawk, like at least during the startup phase, we aerate the reactors for a little bit of time, and then we stop aeration to help the anammox bacteria catch up. So like during that time, just to keep the reactors mixed, the mixers go on. So the mixers come on when the air is turned off during startup.
And to piggyback on Angina's operation of her reactor there at Tomahawk Creek, typically, like the mixers are used for the most part during startups and during low flow and load scenarios. and stuff. So once you get design flow and loads coming in within your reactor, most of the time will be going under the aerobic condition, using air, having air on, so the mixers would not be used and stuff. But the mixers primarily are used during the low flow and load time frames, which is typically during startup, or if you have varying dewatering schedules where you're having to catch back up after a couple days shutdown type thing.
Okay. And so Eric states that I am professionally looking for a heat source that derives from wastewater, like waste to energy. I guess his question is maybe looking for recommendations. Is that right, Eric? Yes.
Yeah, I'm not sure what the actual question is.
Okay, so I guess he's just looking for recommendations. He's professionally looking for a heat source that derives from wastewater, like waste to energy. I don't know, Eric, if you want to restate that to where it's a little bit more clear about what your question is. And as you do that, I'm going to move on to David. You mentioned you can batch feed the reactors. Would a constant feed provide better performance removal?
Go ahead, Angina.
Yeah, I can talk about Tomahawk on this. So at Tomahawk, the ultimate goal is to feed those reactors on a constant feed basis. We're still going through the startup process, right? So we are trying to make sure that we keep feeding those reactors intermittently to make sure that we have enough volume of flow available to feed these reactors over the entire day. Additionally, during the startup, my understanding is that the bugs need the flow, like to help the bugs process the food that's coming in and help them grow slowly. Intermittent mode of feeding is preferred over constant mode, but yeah, ultimately the goal is to get a constant flow of feed to the reactors.
All right, let's see. And so Eric is going to clarify himself, I believe. Aren't there wastewater processes that produce excess heat?
I can try and answer that. I think Eric's trying to talk about like focus on the heat production from biogas. So at Tomahawk, we do use that biogas to heat our boilers. But again, that heat is focused only on digester heating. So I believe the natural gas component comes in as a source of heat for Sidestream because it's in addition to what our digesters are doing currently. Perfect, thank you.
Okay, great. Okay, and so Edward has one question here. Do you have portable pilot systems you can bring in for trials?
Yes, we do have a pilot unit. So we travel with. It's based here where I'm at in Cary, North Carolina, and yes, we do have a pilot ANITA Mox pilot unit available for on-site pilot testing.
Okay, great.
And it's basically it's a container sitting on a 45-foot flatbed, so we can transport it around the United States as necessary.
Okay, great. So how long is a typical startup of the ANITA Mox deammonification process?
As I mentioned, earlier, typical startup is between 2 to 3 months, depending obviously on how much, if your digesters are giving you the ammonia load and the flows that you need and that the system is designed for. Also, another component that startup can be sped up slightly by increasing the amount of seed carriers being used to start to seed the reactor. As I mentioned, we're using 5% of the seed volume for Tomahawk Creek.
Okay, great. And can the ANITA Mox system be designed to be capable of achieving ammonia concentration less than 15 mgl?
Less than 15 milligrams per liter.
Milligrams per liter.
Okay, this is a side stream process. So yes, you're rarely going to see, you're not targeting reducing the ammonia from the side stream that's being returned back to the head of the plant. It's not being discharged into out of the plant. You're returning it back to the head of the plant. So typically they're not designed to be able to get effluent ammonia down to that level.
So Sam, just to extend what Daniel mentioned, when you look at it in terms of load, when the side stream process treats less than 1% of the influent flow, and the ammonia concentration of 15 milligram per liter translate to like a very, very small percent of the influent load. So the target here at Tomahawk at least is to get to about 150 milligrams per liter of ammonia going back to the head of the plant. Again, that translates to about 2% of the influent ammonia load, and that it flows through the BNR process. So the nitrification process takes place in there, but getting to a really low effluent ammonia number out of the side stream would require adding more chemicals, I would assume, like alkalinity supplementation, etc. So the goal here is to get to about 150 milligram per liter.
And angina, and just to kind of piggyback on that a little bit, there has been testing done. There's no installations yet using the anammox bacteria for mainstream treatment. It's been pilot tested by us being able to get down to ammonia concentrations in the mainstream to 15 milligrams per liter. But I was relating it to the side stream part of the design. But yes, there is. It is capable of using the ANITA Mox as a mainstream ammonia removal tool. I know that's the holy grail for everybody that's been trying to achieve that. There's been numerous publications on that over the last 5 to 7 years.
Okay. So we also have a question from David who says, do you think you will have a need for supplemental carbon methanol for the BNR with this or no?
I can take that for Tomahawk. So we've noticed that with this process, with the Sidestream deammonification process, the ammonia load coming back to the head of the plant reduces down to like 2 to 3%. Because of that, there is no additional carbon that is needed over what we are already looking at through our process. So to answer your question, because of this, there is no additional carbon requirement on our BNR process, in addition to what we are already using.
Exactly. It's not going to cut out all of your BNR carbon requirement. And so just this new stream is going to be able to reduce any additional carbon that would be needed.
Okay, and so we've got a funny in the chat. Is there a heat exchanger? Just kidding.
I got to brush up on my heat exchanger language and studying.
Are you able to discuss blower control via DO or pH levels?
We have various methods of control. for our aeration system. There is a DO control option there, and also there is a pH control option available within to control the ANITA Mox process. So, and I think both of those options are available for at Tomahawk Creek. I'm not exactly sure which one's being used right now in China. I'm not sure which one's being used right now. I should know, but I don't.
Yeah, so there is a pH control. So the aeration stops with when the pH reaches a certain level. So that is there, but again, the DO is also being constantly monitored in those reactors. So yeah, there is a pH. The controls is off of pH, but again, the DO is getting monitored all the time.
Okay, we still have just a few more minutes if anyone wants to pop any additional questions into the chat. You may have mentioned the responses to a couple of questions that I have here. How does the ANITA Mox system react to inactivity?
Just the inactivity of the system. You can some of the resiliency of the process. You can once your system is shut down, you can return to your normal flows and loads to your process. You're able to achieve your percent removals typically within 8 hours, so roughly a shift. And also, as I mentioned, there's a vacation mode that can be used for multiple days of inactivity, where you're turning air on and off periodically within the reactor until feed is restored.
Okay. And how does the ANITA Mox system handle polymer overdoses?
Polymer overdoses, which happen, I don't say frequently, but they do occur with some regularity in dewatering, in older dewatering systems. So the process, it can rebound within 24 hours. So you're able to, once that polymer overdose system load comes through the MBBR ANITA Mox reactor, once it passes through, your percent removals will go down, but they'll come back up within 24 hours, between 18 to 24 hours. You're able to achieve back to your normal levels of ammonia removal. So like I said, the key is that all of your biofilm is attached to the carriers. So all these shocks and upsets and inactivities, the system can withstand these things. And you may have slight reduction in percent removals when you initially start it back up, and will bounce back to your normal percent removals within a shift to a day, depending on the condition that you put the system under.
Okay. Does the system require feed flow equalization if you have a varying influent ammonia concentration? How variable is the performance without EQ?
We typically, EQ makes a stabler operating system. Obviously, you would like, with various dewatering schedules, people say, yes, we dewater 24 hours a day, 7 days a week. And yes, theoretically, you should be able not to have an equalization basin upstream. But we found that having an equalization base, a small equalization basin upstream, it makes for a smoother operating system, that you're not stressing the anammox bacteria as much when you're having a steady flow coming into the reactor, flows and loads coming into the reactor. So we would say it makes a better operating system. Not to say you don't have to have an equalization, but it makes for a better operating process having equalization.
Okay. And how much should the feed alkalinity concentration be optimized system? You never have to supplement the alkalinity for Tomahawk.
Yeah, at Tomahawk, we still did not have to use our alkalinity. So our alkalinity coming into the process is about, I'd say 1,500 to 2,000 milligram per liter. And that pretty much has been adequate to do the desired level of nitrification, I'd say deammonification within the Sidestream process.
Okay. And we've got one last question here. Are there any upstream parameters that you monitor that would indicate the concentrate would kill the bacteria?
So I can tell you my experience with Tomahawk. So during our initial startup phase, the one parameter that we were tracking closely was the soluble COD concentration in the centrate. And my understanding is that we don't want that concentration to be too high compared to our ammonia concentration, just so we give the anammox bugs that much time to grow quickly and outcompete any other heterotrophs. Yeah, just making sure that the ratio of that soluble COD to ammonia is less than, I think, 1 was what we were trying to target. And there's alkalinity. Other than those two, I don't know, Daniel, is there anything else that?
Exactly. You hit the nail on the head, Angina. But with regards to the soluble COD, we see that type of fractionation as an issue that can cause some competition within the ANITA Mox reactor in THP centrate. So that's inherently one of the things that we're monitoring and that we design for with regards. But having I'll say typical anaerobic digesters with dewatered centrate from non-THP centrate. This is typically we don't see any issues. We don't see those really high soluble COD levels. But it's not going to harm the bacteria and stuff. It's just going to cause some competition within the reactors. So you're going to have some operation. You'll have to maintain. You have to focus on your system a little bit more while you're seeing that type of high COD coming in. But it's not going to kill the system. It's just going to make those bugs a little less efficient.
Okay, this was great. I don't see any additional questions in chat. And Daniel and Angina, would you all like to make any comments before we close it out for today?
Yeah, I'll start by thank everyone for joining in. And like I said, typically we don't. There's not enough time sometimes to answer questions, so I'm really grateful that we had a good portion of time to answer some questions about the process.
Yeah, I would just reiterate what Daniel said. Thank you all for coming in or listening in. Our contact information is on there. So if there are any further questions that were not answered, just let us know and we'll be happy to answer them.
Yeah, this was great. And I just want to thank the both of you for such a great presentation. And I'm very happy that we had so much time to answer so many great questions as well. I want to thank you all, Angina and Daniel, for a great presentation. Thank you to the attendees. And definitely thank Viola for sponsoring today's event. This actually concludes today's e-showcase. Thank you all for attending. The recording will be available at webfiresguide.wef.org. We will send all registrants an email tomorrow with that link. And please visit our event calendar to sign up for future events.